Hey guys, so I wanted to quickly give a demonstration of one of the practice exercises for a problem that involves Jordan canonical form and also using the fundamental solution matrices, and use that as a chance to kind of talk about those things. So we're going to do 2e from 2.1 toward 12.1, and we need to solve the equation x prime equals ax, where a is given here, and we have an initial value given as well, and we need to find the solution to this problem. So the first thing we need to do is find the eigenvalue. So what we're going to do is obviously find the determinant of a minus lambda I and set that equal to 0 and solve for lambda. So I did most of this stuff beforehand, so I'm just going to kind of go through it. This is all irrelevant. So we need the determinant of this guy, which, as I calculated here by expanding along the first row. How did I do that? Well, the first column. I used the first column because it's mostly zeros, which is nice. And so it's just this coefficient times negative 1 to the I plus j, which is 2, times the determinant of this minor, and it turns out that the only part of the minor that matters is this this thing. So that's the entire determinant, and it collapses down to just this, which means our eigenvalues are only 0 and 1. Now, when we find that there's only two distinct eigenvalues, we pray that means that both eigenspaces have dimension 2, but that's not always the case, and it's sadly not the case here. So let's work on eigenvalue 0 first. So we want to row reduce a minus 0i, which is of course just a. So if we row reduce a, we get this matrix with the help of Wolfram alpha to get rid of mistakes. And what does this tell us? It tells us, sadly, that we only have an eigenspace of dimension 1 for corresponding to eigenvalue 0. So we've got to move on to look at a minus 0i squared. So if we square it, we get this guy, and then we row reduce down here. So now, of course, our kernel is now two-dimensional. And from this row reduced form, we can read off what the span of that kernel is, and this is our span. Now, looking just at the row reduced form of A, we see that this guy is actually an eigenvector of a minus 0i not squared. So it's in the kernel of a minus 0i, so it's in the kernel of A, which means that we want to use this guy as our eigenvector with eigenvalue 0, and this guy as our generalized eigenvector corresponding to it. So if we're going to keep, so I have this P matrix written down already because I've already calculated it, but just to tabulate, so that would start us off by putting the eigenvector in the first column and the generalized eigenvector in the second column. Okay. So then we have to do eigenvalue 1, so we calculate a minus I times 1, and we get this. We reduce it, we get this. And once again, we have a one-dimensional eigenspace. Very sad, but whatever. We move on and square it. And now, once we row reduce it, we will see that we have a two-dimensional kernel. So that's great. What is the span of this kernel? Well, clearly this entire thing, we have this guy. And we also have that this is another eigenvector by looking at these guys. So now let's look back at just a minus 1i. And when we row reduce that, we see that 1, 0, 0, 0 is also an eigenvector, is also in the kernel of a minus 1i. So that can be our eigenvector, and then our generalized eigenvector can be this other guy. So then we'll shove those both back in P, and let's look back up at P. And yep, we're good. So here's our eigenvector, and here's our generalized eigenvector corresponding to lambda equals 1. Okay, what does our j look like? Just, I guess without saying it, I've been assuming that our j, well, no, we had to calculate the dimensions of the eigenspaces in order to calculate it, but here we have that the j is 0, 0, 1, and then 1, 1, 1. This is our Jordan canonical form of the matrix. Okay, so we've done all of that work. What do we do with it? Now that we have that, now we have our A diagonalized or Jordan canonical formified. What does that mean? What does that have to do with our problem? Well, so we wrote A as this. Now we have a couple of things that we happen to know that we went over in lecture and stuff, and it's that if that J is the Jordan canonical form of our matrix, then X solves this equation, where X is the matrix that we can construct from the Jordan canonical form that we calculated. So how do we do this? How do we recall from lecture that if we have lambda, 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 1, 1, 1, 1, 1, then the X corresponding to this Jordan block, or the X block corresponding to this Jordan block, is going to be e to the lambda t distributed over 1, 1, 1, or so, 1, 1, 1, 1. I'll draw more so I can use more, say more terms. And then t, 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 dot, 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 1/2 t squared, 1/2 t squared, 1/2 t squared, 1/6 t cubed, 1/6 t cubed, blah, 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 blah. On and on. Taylor things. This is how you write the block of X corresponding to the Jordan block given by this for an arbitrarily large Jordan block. So here we only have nice small Jordan blocks. We only have 2 by 2 Jordan blocks. Now for this block, we have lambda equals 0, and e to the 0 is just 1, so we don't care about that. Or at least we don't have to write any e's. For this one, we have that lambda is 1, so we have e to the 1t, and then we in all of them we have our times 1 times 1 times 1 times 1 times t times t. Okay. So we already showed that. We already know, we memorized how to construct the x vector, and we saw in the lecture notes why why this matrix X solves this equation. So now we're going to use that fact here. So we had our initial problem, x prime equals ax, and we're going to try the solution, y equals p, which is the thing we calculated, times x, this thing corresponding to our Jordan thing, times the constant vector c, times this is our, as in C1, C2, C3, etc., the coefficients of our solution. So let's try that. So let's suppose that this is true. We've done that a lot. And take the derivative of it and see what we get. So if we take the derivative of y prime, well, p is constant, c is constant. X is the only thing that's kind of a function of t. So if we take the derivative, we should get p times x prime times the constant vector c. Yes, right, a little side note. So I wanted to make a little side note about these writing solutions like this versus little x, that's a vector, times a x little vector. So if I have a linear combination that looks like this, I have c1 times e to the lambda 1t times v1. This is a vector. Think of this as a two-dimensional vector for now. This is also a two-dimensional vector. Let's say I have solved a sum problem, not this problem, and I've come up with a solution that looks like this. Well, I can also write that solution as this matrix times this vector. So I take the first component of V1 and the second component of V1, and I put them in a column here, and the first and second components of V2, and I put them in this column. And if I then multiply them by this constant matrix, or sorry, this constant vector, then I get back the solution that I wanted. I get this guy back. It's just another way to write it. It's just another type of bookkeeping. So when you see all of this stuff where all of a sudden we're solving for matrices instead of vectors, just know that the bookkeeping has just changed a little bit. So when you see stuff like where is it? This f prime equals AF. We'll get to this topic in a second. Just know that using the capital F matrix as a way of writing the solution and posing the problem it's just a different way of bookkeeping. Just a different way to bookkeep things. All right. So where were we? Okay, so we're trying y equals this, and we're seeing what happens. Because we know what this is, we know what this is, we know what this is. Let's take its derivative. Let's take its derivative and see what we get. Well, y prime is equal to p x prime c. But notice also that if we multiply a by pxc, so we're trying y equals pxc. If we multiply this by a, I don't know, maybe we'll get the derivative of y, and that's how we're checking whether this is a solution. So if we multiply it by a, we know that a is equal to pj inverse. That's what we did by Jordan canonical forming the matrix. So, but p cancels with p inverse, and so a times pxc is equal to pjx. Okay, but what do we know about x? The special thing about x is that it solves the equation jx equals x prime. That's the whole point of x. So we take that fact. Hold on. Right, not here yet. Okay, so we take that fact and we can replace jx with x prime. And what do you know? Px prime c is what we got for y prime. That's the same thing. So it's y prime. So what this all means is that y prime is equal to ay. Okay, fantastic. So that means that y is a solution. Okay, and you can see the lecture notes for why has to be the solution as opposed to some solution. Why the solution is unique. Okay, so y is pxc, where y is the solution to this problem. Now let's look at the initial condition. So if we plug in 0 for y, because this is a function, this x has a bunch of t's in it, so this is just one big function. We could write this. If we plug in 0, this is, the only place we have t's is here, so it's equal to p times x of 0 times c, which is equal to x of 0. So x, right, we just, when this from the initial condition. And the initial condition is that this is 1, 1, negative 1, negative 1. This is what was given to us at the beginning of the problem that we have to solve. So we're given this. We're given y of 0. It's just the initial condition. But what's x of 0? Well, one very nice property of these x's is that as soon as you plug in 0, you get the identity matrix. Because this is 0, this is 0, and if we have bigger stuff, then it's all just multiplied by powers of t, and we plug in 0 and we get 0. But this stays as 1, because e to the 0 is 1, and we just have 1s and e to the 0s, and therefore just all 1s. So x of 0 is just the identity. That's great, which means that the initial condition is just equal to p times c. So then we can multiply both sides by p inverse and get that c, our coefficient matrix, is just equal to p inverse times x of 0, our initial condition. So then y, we can replace c with p inverse of x0. Y is equal to this, where we know everything. So this is great. So now we have written the answer to the problem in terms of things that we know and have already calculated. Okay, so I went ahead and calculated px times p inverse. It's this. I used Wolfram alpha to do that for our x that we calculated above and our p and p inverse, etc. It's equal to this times this initial condition vector, and we get this. And this is the final solution, equals x of t, where I'm just writing a lowercase x now because that's the variable that we were given at the beginning of the problem. Yeah, it's confusing when we have these x's and these y's and we're switching around what they mean, but yeah, sometimes we'll use different letters to represent different things, and that's just part of how it goes. Okay, so the fundamental solution matrix. So that is equal to this thing, px p inverse, and in our case it's equal to this big guy. So we know that it solves this with this initial condition. Okay, why? Because so the fundamental solution matrix, it's equal to px p inverse. If we take the derivative, we get this. I'll use the laser. We get this because x is the only thing with t's in it. P and p inverse are constants. We know that x prime is equal to jx, so we can replace that. Now what we can do is insert p inverse times p. So this is just equal to the identity, so we can just insert this in this section. Then we can, matrix multiplication is associative, so we can separate out this from this. And this is equal to our original f on the left, and this is equal to a, actually. So this is af. So what do you know? We took the derivative, and we got f prime equals af. So that's true. And also with this initial condition, because x. So if we plug in, if x of 0 is the identity, and that leaves us with p times the identity times p inverse, which is also the identity. So f of 0 is the identity. So also notice, what does this have to do with matrix exponentials? Why on earth is f equal to t to the a? Well, a is equal to, how do we see this? A is equal to p times j times p inverse. You guys have been through this before. What is a matrix exponential? Well, it's defined as this series. From this series, we can take out a p and a p inverse from both sides of every single term. Because just recall that p times p j p inverse dot 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 dot. These all cancel. So this is p j to whatever power, blah blah blah. Just to go over that, make sure we're all on the same page. Yeah, so that's equal to this guy. But what is this guy? Well, let's expand the middle part into a series, and we get that it's equal to this. And this, I'm not going to show it in full, but this is actually equal to x. Because when you take a Taylor series like this and raise this guy to powers, we've been looking at powers of Jordan canonical form of matrices, we will get that thing that we wanted, e to the lambda t, e to the lambda t, e to the lambda t, t e to the lambda t, t e to the lambda t, 1/2 t squared e to the, you know what I mean, and on and on. That's just what happens when you take this series. Okay, and that's where I will end with this problem. So we solved this problem and then talked a little bit about what the fundamental solution matrix is and how to use it to solve problems. All right,